Hi guys, in this video we're going to be going over chemical equilibrium and the equilibrium constant. Basically we'll go through some definitions, listing factors affecting chemical equilibrium. We'll explain what the equilibrium constant is, factors that affect it and how to calculate it. We'll also explain the significance of high and low values of the equilibrium constant. Alright, so let's go through some definitions first regarding chemical equilibrium. Okay, so open and closed systems firstly, what are they? An open system continuously acts with its environment while a closed system is isolated from its surroundings. Very straightforward. A reversible reaction is a reaction. A reaction is reversible when products can be converted back into reactants. Alright. So an example here is given of a reversible reaction. H2 plus I2 equals to producing a HI is the forward reaction, and it's always written from left to right as shown here. It's always written from left to right. Let's change the color. From left to right. And the reverse reaction is HI is H2, it gives us H2 and I2. That's the reverse reaction. It's always taken from right to left. But it's very self-explanatory, just the definition is fine. Now getting to what chemical equilibrium is. It is a dynamic equilibrium where the rate of the forward reaction equals the rate of the reverse reaction. Right? So now you know what a forward reaction is and a reverse reaction. That was defined here, forward reaction and reverse reaction. And when these rates equal each other, that is called chemical equilibrium. And there are three factors that affect it. One is pressure, two is concentration, and three is temperature. And that's pretty much what you need to know with regards to chemical equilibrium. Now we're going to move on to what's called the equilibrium constant. Now, the equilibrium constant relates to concentration of the reactants and products at equilibrium. So, same equilibrium mentioned above here, this equilibrium, same chemical equilibrium. So now the equilibrium constant relates to this, the products and reactants at equilibrium, and it's calculated as shown here. So if you have some product, AA plus BB gives us CC and DD, where A, B, C and D, these are all elements, so it could be carbon, hydrogen, oxygen, whatever, and A, B, C, D are just placeholders or coefficients of those compounds, right, or molecules. So this could have been 3A, so it could have been 3A plus 2B to give, there's a reverse, the other way around, that, 2 and 3, whatever. Just an example of what it means. Okay, and using these coefficients and the molecules itself, we can get the equilibrium constant. There's some important notes here that A, B, C, and D are molar concentrations of the substance. So it's these brackets here, these brackets like so. These indicate that it's the concentration of whichever element is inside. So if you had, for example, that would be the concentration of hydrogen, and then yeah, that's pretty much it. And then obviously the exponents will be coefficients. And it's important here. That's one other thing that you really have to remember is that in this case we're going to leave out liquids and solids and only focus on our gases. That's the important thing in this type of question. So we're going to do one quick example of this, an easy one, and then we'll do a much more difficult one afterwards. Okay. So we're given SO2 plus NO2 to give you NO plus SO3. The concentration of sodium oxide, sulfur oxide, and nitrogen oxide are given. So this nitrogen dioxide and nitrogen oxide. These are all given, the concentrations are given. So now we're required to determine your Kc. Your Kc is the equilibrium constant, yeah? Okay, so let's work it out. So first step is we write the equation for Kc. So we have Kc here. Remember the equation is Cc, brackets, it's the concentration of D to the exponent of D all over A, that's your reactant, to the A, and the concentration of B to the B. Okay. Now we notice that, let's look at the coefficients of this. There's a coefficient 1, it's 1 there, it's 1 there, and it's 1 there. So basically we want the concentration of, you can name this as A, B, C, and D. We're going to have the concentration of C, okay, let's make it NO, and now to the 1, plus SO, not SO times SO3 to the 1, all over A is given as SO2, and the coefficient is 1, and NO2, and the coefficient is also 1, right? So now we're given all the values, so it's all we have to do now is substitute. So we have Kc is equal to, substitute, we have 4 times O2 times 0.2 times 0.1, which gives you an answer of 4. And that's the equilibrium constant. That's quite straightforward. I mean, it wouldn't have any units because the units will cancel out. So that's pretty much how you calculate a very simple example of the equilibrium constant, Kc. And one point now, so that was a simple example. So when you're doing more complicated calculations, we draw what's called a Rice table. Each letter in Rice stands for something, but it's an easy way to organize information in equilibrium calculations. So let's do it. So this is Rice, right? So this table here just indicates what each letter in Rice is, and then afterwards I've shown the steps to calculate it, and after that we're going to do an example, right? So R stands for reaction, it's just the balanced equation. Then I is initial quantity, we just calculate the number of moles of each reactant at the beginning of the reaction. Then C stands for change, it's how much the moles of reactants and products change between the beginning of the reaction. Then finally we calculate the equilibrium quantity. It's the product of reactants and products at equilibrium. And then equilibrium concentration, to calculate Kc, that's equilibrium concentration, right? You need to calculate the concentration of the reactants and the products at equilibrium. So let's just go through the example with placeholder values and each step by step, and then we'll do a practical example afterwards. So first step will be to fill in the balanced equation like this. So if you're given this here, this is the equation given. First thing is to fill out your value. So there's a balanced equation, it's given like that, right? Then you're given an initial number of moles, right? So it says initially, then in the initial row, fill the number of moles of each substance present at the beginning of the reaction. So we're saying, for example, there's 0.3 moles of A, 0.7 moles of B, and no moles of the product. So we fill that in the table, right? Initial moles. Number 3 is to go into the change in moles, right? The change in the change row, you have to fill in the number of moles of reactant used or the number of moles of product formed in terms of X. We use the balance equation for this. If dx, for example, if dx moles of D is produced, bx moles of B will be used. So I also want to note an important part here. Look at the values, right? So these values are negative and these values are positive. It's because whatever's in the reactant A is being used up to produce the product C, and C and D, and similarly for B. That's why it's negative, and that becomes because these give away the reactants. These reactants give away their moles, and the products accept them. That's why it's positive and negative, right? Then in equilibrium row, you have to fill in the number of moles of each substance present at equilibrium in terms of X. For example, there will be 0.3 minus AX moles of A at equilibrium. So basically you just subtract the two here. It's just a subtraction of these two values, and you get that. Or you actually add the values because you add the values because negative and positive. So that's why 0 plus dx gives you dx, or 0.3 plus ax gives you 0.3 minus ax. That's basic maths. And then you use your extra information to calculate x and then finish the table off. So and then you just calculate, you fill in the last row of the concentration of each substance at equilibrium, and you calculate this value, right? So we'll do the example now. Might be a little bit long, but if you can get this right in the exam, you get a lot of marks. And so I'll just go through one so it makes more sense, and I'll leave a link in the description to more examples that you can try it yourself. Right. So it says 1.4 moles of NH3 is introduced to a sealed 2.22 decimeter reaction vessel. The ammonia decomposes when the temperature is increased to 600 Kelvin and reaches equilibrium as follows. 2 NH3 to ammonia gives you N2 and 3H2, that's hydrogen and nitrogen. When the equilibrium mixture is analyzed, the concentration of ammonia is 0.3 moles per decimeter cubed. So the concentration is given, right? They want us to calculate the concentration of nitrogen and hydrogen in the equilibrium mixture. Okay. And then secondly, to calculate the equilibrium constant for the reaction. So actually the first step would actually be to write to write down your rice table, because it's going to be a long question. You can see they want so many things. So you just write down rice and you draw up a table. I have already done it, like so. And then the second step after you've done that is to write out the balanced chemical equation as given. So let's go check out the balanced equation. Okay, so we've got on the reactant side, what do we have? We have 2 ammonias, so it's 2 NH3, and we have 1 nitrogen gas and 3 hydrogen gases, right? Sorry. There we go. First part of rice table done. Next step will be to write down the initial quantities of moles given. So initially there's no moles of any of the substances except the ammonia in the beginning, right? So let's write that in. So that means 1.4 and no product. Right. Next step, they want us to find the change in number of moles, right? So that's the next thing on the table, right? So to do that, what we need to do is look at the mole ratio. So like for every, look at the mole ratio. So we got here, if I write it here, this is screen, just for that. So the third step, so first step, second step, third step now, right? The change in mole, right? So the mole ratio of ammonia to nitrogen gas, so it's like ammonia NH3. Let's make this a little bit, sorry. So let's just look at the ratio here. Now we just look at ratios NH3 to N2 to H2. The ratio is going to be 2:1:3. Right. So what this means is that for every 2 moles of NH3 used, 1 mole of nitrogen is used and 3 moles of H2 will be formed. Right. So if the number of moles of NH3 decreases by 2x, then the number of moles of N2 will increase by 1, and the number of moles of H3 will increase by 3. Right. So that's the ratio. So the third step is to change in moles. Basically means to find the ratios, and then to add x to it, right? Because we don't know, or we still have to be asked to calculate that. So like I mentioned, this will decrease by 2. We look at the ratio, and then we can say from the products we can get reactants. Remember that's why it's negative. And then this is going to increase by 1. That's the ratio, and this will increase by 3. And this is both x's. It's both x's, right? Okay. Right. Let's see. The next step will be to find the equilibrium quantity, right? So we have to get the number of moles of the substance at equilibrium. We take the number of moles initially, and you add the change in number of moles in terms of x, right? So what we do is we just sum the two that's given, right? So we just say, in this case it's going to be, let's just do that, 1.4 plus minus x2, you're just going to get minus x2. We've got 0 plus x1 is just going to be x. and let's put a plus just to make it clear, and you're gonna get plus 3x in this case, right? And then the last step really is, or the next step, that's not the last step for this table, is to calculate the value of x, right? So let's go back up to our question and see what else we're given, okay? So we're given, okay, we've been given that we have the concentration of ammonia, we've given the number of moles of ammonia, and we've given what it's sealed at, right? So it's a pressure, I think, right? Oh, that's just the quantity of the vessel, right? Okay, anyway. So we have all of these. So in order to calculate number of moles, given that we have the volume, right? Volume in decimeter cubed, and we have the concentration. So we can calculate the number of moles. We don't have to look, we're not given grams or anything. It's to use N is equal to M of M. In this case we use the formula for concentration, C is equal to N over V. And from here we know that N is equal to CV. That should be a capital C and a small c. Okay, just CV, don't worry. And then so we know the concentration. Concentration was given as 0.3, right? Sorry, it's given as 0.3, and the volume of the vessel it's in is 2. Right. So this is equal to 0.6 mole. So that's quite so straightforward and simple, right? So from the rise table we see that there are 1.4 minus 2x moles of NH3, moles of an ammonia at equilibrium. You can see right from here, this is where we're checking from, right? You can see that's how many it is. Therefore we can say that we have 0.6 is equal to 1.4 minus 2x. Therefore we can say that 2x is equal to 1.4 minus 0.6, just changing the subject of the formula there. And finally we can say that x is equal to 0.4 mole. Okay, and then from there, so we have the number of moles. So we calculate x, right? So now that we have x there, we can calculate the concentration of N2 formed at equilibrium, right? The nitrogen. So we go back here to the table, look at nitrogen. So what we require to do is to calculate the concentration of nitrogen and calculate the concentration of hydrogen. So from that, we're going to get that from the equilibrium quantity, right, in moles. So we have x and 3x. Okay, so let's calculate that. So we're now we're calculating N2 concentration at equilibrium. Okay, so we saw from the table, from our rise table, that the number of moles of nitrogen, this is right here to make it easy for you, nitrogen and hydrogen, right? Number of moles of hydrogen of nitrogen is just x at equilibrium. So we can just say that number of moles of nitrogen is equal to x, which is equal to 0.4. Sorry about that. It's equal to 0.4 mole as we calculated x. So from here we can use the same concentration formula. Concentration of nitrogen as what we required is equal to number of moles over volume. The same container vessel is going to be used of 2 decimeters cubed, and we're going to get 0.2 mole per decimeter cubed. Right. So that's one part of A done. Just finally took a while to see how long it took to get A. And then now we can calculate the concentration of hydrogen. This next one is quite simple as well. So this is calculate concentration of N2. So next is to calculate hydrogen gas concentration at equilibrium. Alright, so this is equal to, this is the concentration of hydrogen. Okay, so the number of moles of hydrogen gas is equal to, sorry about that, is equal to 3x. So we got 3x, it's equal to 3x. From our price table, we see it's equal to 3x, which is equal to 3x, we calculate to be 0.4, and this is going to just give you 1.2 mole. Okay, so we have number of moles. We use the same formula, calculate the concentration of hydrogen is equal to number of moles over volume, which is equal to 1.2 over the same size vessel 2, and we're going to get here 0.6 mole per decimeter minus 3, and you know, just like that. So concentration of hydrogen. Okay, that's it. It's very, very straightforward, and if you want now, you can just fill it in our table. Okay, let's just see. We calculated, what have we calculated, right? We calculated that we had, okay, we were given 0.3. There was a concentration of ammonia given. Sorry about that. Let's just do that. 0.3. Okay, we calculated nitrogen to be 0.2, and we calculated hydrogen to be 0.6. There we go. That's your rice table. It's completed. We have the concentrations of all the substances. And now the next question. So the first question was to calculate concentration of nitrogen and hydrogen, and the next one was to calculate the equilibrium constant at 600 Kelvin. Okay. So what's our reactant? Our reactant is NH3. Our products are N2 and H2, and notice the coefficients, right? So let's do that now. Let's do it. So we know that equilibrium constant is going to be equal to products over, so that's your products to the 3 over reactants NH3 to the 2. So where do we get this from? So we take our, remember, we just did that now. This formula here we used. This is the formula we use. It's the same formula, products over reactants. And we see that the coefficients from each one is used in the top here. We can put the 1 if you'd like for nitrogen, doesn't make a difference, but that's how it is. And we substitute the concentrations of each one. So the concentration of nitrogen we calculate to be 0.2, we calculate this to be 0.6, we cube that, and it's 0.3, and we get the Kc to be equal to 0.48. And that's it. A bit of a long calculation. That's what you can expect in this sort of equation, this sort of in this section. It's a little bit long. That's quite a bit to do. But that's how you calculated the equilibrium constant. There's one more thing I just want to what does it mean? What does the equilibrium constant actually mean? So I have a bit of information here about that, right? So if you have a high equilibrium constant, it's greater than 1, it means the equilibrium is to the right and there's more products than reactants, right? There's a high concentration and it's a high yield. If the equilibrium constant is low, close to 0, it means that the concentration of reactants is high, the equilibrium lies far to the left, and the reaction has a low yield. That's pretty much how you do this sort of question. I know it's a bit long and tedious, but I'll post a link in the description for more examples to help you understand more. But yeah, that's about it. Thanks guys.